Remember the old days of watching DVD on your TV? As a child, you had most certainly been fascinated by the DVD screensaver bouncing around in the screen. You probably used to wait for it to hit the corner. Sometimes it did, most of the time it didn't. In this video, I will dissect your childhood fantasy with maths and show you how to know if the logo will hit the corner or not. And if it does hit one corner, or corners, which ones it would hit. Well, mathematicians are cruel at heart. They feel a constant urge to thrust maths into everything. Here on screen is a simplified animation for the screensaver. The big rectangle is just TV screen and the small one is the logo. Now you will say that the screensaver is not a rectangle, and that's right. But while detecting collision with the border, a rectangle is assumed surrounding it, known as the collision rectangle. So in theory, the logo does behave like a rectangle. First, think to yourself, on which factors does the bouncing of the logo depend on? It's easy to notice that these are the dimensions of the screen, the dimensions of the logo itself, the starting position, and the initial direction of velocity. Since the magnitude of the velocity is constant, the last point is just equivalent to the horizontal and vertical component of velocity. First, in order to make our life easier, I'll make some assumptions. First assumption is that the height and the width of the screen and the logo are all integers. This is a valid assumption. Why? Even if measurements are not exactly integer, with suitable choice of units, which is often pixels, they can be made integer. Second assumption is that instead of a rectangle as the logo, we will consider it as a point. Now you might be furious. Thinking the logo as a rectangle was acceptable, but now a point? But I promise, you will see in a moment that the rectangle case is equivalent to the point case. And the last assumption is that the horizontal and vertical component of velocity are equal, which is same as saying the point was projected at 45 degrees. With these assumptions in mind, let's get started. We start by naming things. Let's call the screen ABCD and introduce our handy Cartesian coordinates with origin at point A. Now this wasn't absolutely necessary, but when talking about positions in a plane it often helps. Next we name the dimensions. We call the width of the screen capital W and the height of the screen capital H. And the starting point is A, B, and the coordinates of the corners turn out to be 0, 0, capital W, 0, capital W, H, and 0, H. First, we start with the simple case of starting from the origin, which means A equals 0 and B equals 0. Now, as we have resolved the velocity vector in the horizontal and vertical components, these two directions can be considered independent of each other. Let us concentrate first on horizontal direction. In order to reach a corner, the x-coordinate of the point must be either 0 or capital W. Note carefully that if the x-coordinate of the point has become 0, it means it has travelled a distance which is an even multiple of capital W. Similarly, if its x-coordinate becomes capital W, it must have travelled an odd multiple of capital W. This is going to be our insight for finding out the condition for hitting a corner and finding out which corners it hits. So no matter be the corner, if it hits one, its distance travelled in horizontal direction must be a multiple of W. Now we apply the same idea to the vertical. The y coordinates of the corners are either 0 or capital H. Similarly, if the y coordinate of the point becomes 0, it must have travelled an even multiple of capital H. And if it becomes capital H, it must have travelled an odd multiple of capital H. So no matter the corner, reaching 1 means it has travelled a multiple of capital H. Now we can look at both the directions together. Reaching a corner means both the previous cases simultaneously happening. Now since the components of velocity in both the directions are same, distance travelled in both the direction at any instant is also same. So reaching a corner means some multiple of capital W, which is the distance travelled horizontally, must equal some multiple of capital H, which is the distance travelled vertically. So we can write D equals P times capital W equals Q times capital H. Here D is the distance travelled in horizontal and vertical direction, and P and Q are integers. So we quickly discover two things. First, can we find some P and some Q for which this will be satisfied? The answer is yes. P equals capital H and Q equals capital W trivially satisfies the equation. So our first insight is that if the point starts from the origin, it will always hit a corner. Next we see that the distance d is divisible by both capital W and capital H, which means it's also divisible by the LCM of these two. So the point must travel a minimum of the LCM of capital H and capital W before it can hit a corner. Which corner the ball hits depends on Q and P, especially if they are odd or even. P is even implies that the point travels an even multiple of capital W horizontally, which means the x-coordinate will be 0. So it will hit either A or D. Similarly, P odd implies it will hit either B or C. And similarly, depending on the parity of Q, we can pinpoint the exact corner. Here's a little table. Alright, now we can move on to the general case of starting from any A, B. It's now easy. See that reaching a corner horizontally means the distance traveled will always be A short of A multiple of W. And reaching a corner vertically means that the distance traveled will always be B short of a multiple of capital H. So just like before, our equation this time becomes D equals P times W minus A equals Q times capital H minus B. Rearranging the terms, we have P times capital W minus Q times capital H equals A minus B. This is a Diophantine equation in P and Q. Now if you don't know what a Diophantine equation is, I will leave a link in the description. Also, I can probably make a video on Diophantine equation. Anyway, like the previous case, this time we might not get a solution always. In fact, in order for this to have a solution, the GCD of capital W and capital H must divide A minus B. And indeed, that is our condition. In order to reach a corner, A minus B must be divisible by the GCD of capital W and capital H. Let's take an example. Here I have taken capital W to be 10, capital H to be 4, A to be 6 and B to be 2. So if we solve this, P turns out to be 2 and Q turns out to be 4. So it will hit the corner A. Let's see. And there you go. Alright, at this point, I will leave two exercises for the viewers. First question is, can the point hit the same corner twice without hitting any other corner in between? And the next question is it possible to hit all the 4 corners? Go ahead, think about it. Okay, now we can look at the case of the rectangle logo. This one, as I promised, can be reduced to the point case. We call the width of the logo small w and the height of the logo small h. Indeed, we look at the bottom left point of the logo. Notice that the whole screen is not available to this point. Indeed, it can only reach up to capital W minus small w in the right and capital H minus small h upwards. So actually, this point itself travels in a rectangle of lengths capital W minus small w and capital H minus small h. And if the logo hits a corner of the screen, this point also hits a corner of the effective screen of this point. So we can think of this case as a point in the screen of capital W minus small w and capital H minus small h. Isn't that convenient? So we just replace capital W by capital W minus small w and capital H by capital H minus small h in our previous condition and find the condition that A minus B must be divisible by the GCD of capital W minus small w and capital H minus small h. Now let's see an example of this case. Here I have taken capital W to be 10, capital H to be 6, small w to be 2, small h to be 2, A to be 3 and B to be 3. If we solve this equation, we will see that for any natural number n, P equals N and Q equals 2N satisfies this equation. So the logo will bounce around between the points A and P. There you go. Your childhood successfully ruined by maths. However, I will encourage the viewers to try the question that I post. Here are those one more time. Can the point hit the same corner twice without hitting any other corner in between? And is it possible to hit all the 4 corners? And finally, a bonus. What happens when the horizontal and vertical components of the velocity are not equal?